this system wave is a standing wave. Standing wave. And as I said here, the confined means both ends is fixed. Okay. And transverse wave and longitudinal wave. Transverse wave and longitudinal wave. Transverse wave is the displacement vector is perpendicular to the propagation of the wave. Okay, longitudinal wave, the displacement is parallel to the propagation of the wave. So most of the waves are transverse wave, but sounds like sound wave is a typical example of a longitudinal wave. Rarefaction and condensation is repeated. Rarefaction and condensation. That is the characteristic of a longitudinal wave. Okay, let's go into the real system which we can apply the wave equations. And the most simple easy to understand is the string. Okay, string under tension. String under tension. That is, there's a string, and only one portion, small portion of the string is going to be shown here. And then from these 2 points, the distance is going to be ds, we're going to say. And then this is the distance, it's going to be the dx, distance along the x-axis. And the distance from here to here is going to be the psi, because this y-axis is going to be the displacement of the particle, and the x-axis is going to be the x, the physical dimensions. So in this system, and then we set this theta, and then there should be a 3 assumptions, basic assumptions, and that has been in the test. One is the psi should be very much less than x in scale, which means the displacement is not going to be much. You know, when you talk about a string, we are going to talk about a very small portion of it, and then you are not going to make a very big waves, very small waves. So that is the psi displacement of the wave is going to be very small with respect to the distance of the particles. And then uniform string along the length of the string, the density, whatever physical variables should be the same, so uniform. And then finally, we are going to assume that it's a harmonic wave, so that the disturbance is not that big, so that we can assume that it's a harmonic wave. Then what we're going to calculate here is that we're going to calculate at this point the force up and force down, okay? And then this force up and down comes from the fact that it has been tensioned with a tower at both ends. Okay? So some part of this tower, the force, tension, is going to contribute for the force for this part going up and this part going down. So we have somehow imbalance. So what we are going to do is that we are going to get the net force at that part, and the net force is going to be the force up minus force down, okay? That is the net force. And then we're going to equate this force with the Newtonian. It should be something like this. F equal to ma, right? And here the mass is going to be density of the string and then dx, the distance in dx. We assume that the ds is almost the same to dx, okay? That is going to be the mass, and here the acceleration is going to be the second derivative of the movement with respect to the time. Okay? So, if you can find this force in terms of x, okay, round psi over round x, whatever, you can find this net force with respect to the x, okay? Then we have a general expression for the wave, because one part is the displacement differential equation, differential with respect to the distance x, and this part is going to be the displacement with respect to the time. So that is the general expression for the wave. So what you're going to do is, this part is already fixed. So all we have to do is we have to find out what is going to be the net force applying to this string, this segment, okay, with respect to the x. And how can you do it? It's not that difficult. First, down is going to be the tangent sine theta, right? We're going to that. That's simple. And then that is the tower, and then sine theta, when theta is very, very small, then that is going to be the ds over dx over d psi. ds is almost equal to the ds. So when the sine theta can be defined just like this, okay? And the force up is going to be the tower, and then the tail expansion of the system, that is going to be round x, round psi over round x dx. Okay? So when you make a subtraction for up and down, then F net, which is equal to down minus up, and that is going to be the round x square, round square, something like this. All right? So, you have to multiply this, of course, by the tau on top. Okay? So, now, what you're going to do is tower round x square round square psi should be equated to the tower, to rho round x round t square round square psi. Dx and dx is going to be rho dx rho dx and dx, and here times dx is going to be the cancel, so that we end up with this equation, right? That is the wave equation. Second order wave equations. And we know the solution, general solution of this, and all we have to do is put some boundary conditions to have a specific answer. Now the psi general solution is going to be exponential I kx minus omega t plus b exponential minus I kx minus omega t. Okay? That is going to be the general solution, so that minus k square psi, you just put the second derivative of this psi with respect to the x, and you have a second derivative with respect to this equation. Now, what is the characteristic of the exponentials? When you make a derivative of that, you are going to be the same. The answer is going to be the same. Okay? In other words, if you make a second derivative of psi with respect to the x, then you end up with k squared, minus k squared psi. That's interesting, isn't it? That is the characteristic of the exponential, by the way. And then you make a second derivative of this, is going to be minus omega squared over psi. So all you have to do is just put these things under this equation here. Then the left-hand side is going to be the minus k squared psi. And then right-hand side is going to be tau over rho. That is a constant, and minus omega squared and the psi. Okay? And then you just eliminate the psi, which is in common on this equation. And then you end up with omega squared over k squared is now going to be the tau over rho. Tau is the tension that we apply externally, and we know that value. And rho is the density of the string. Okay? And then omega versus k is related to the velocity of the system, so that it's going to be the velocity of the system. Now, since this is a constant, we know that this omega versus k is going to be the straight line, and then slope is corresponding to tau over rho, and non-dispersive system, okay, of this wave. You can actually find these solutions depending on the system by using the boundary conditions of the system to get the specific number of the A and B. And that is the wave equation. But sometimes, most of the time, the dispersion relations, omega versus k, is enough to know, to understand the system sometimes. Okay? Because the energy of the system is related to the omega only. Okay? H bar omega is the energy, and the momentum of the system is h bar k. So if you know omega and k, we know the energy of the system, we know the momentum of the system, so that we can have all the we can have all the answers that we need to understand the system. Sometimes we don't have to get the exact solution for the wave. Okay, so most of the systems that you are going to deal with, we just stop by getting the dispersion relations, and we are not going for the actual wave equation solutions for the wave equations. Now, what happens if we fix both ends? Fixed end string. Okay, then we are going to boundary condition. We are going to have a boundary conditions like x is equal to 0 at one end in any time, then displacement should be the 0. And the second boundary condition is that when the other end of the string, x equal to L, at any time, it should also be 0. It should not be displaced. And from here, we can say A equal to minus B in this general equations. Okay? And from this boundary conditions, A e to the IKL plus B e to the minus IKL, and that is going to be 2I sine KL. That should be 0, so that the K should be L pi over L and an integer. N should be 1, 2, 3, something like that. Okay? Which means L is going to be half wavelength and integer multiple. That's interesting. We cannot have values corresponding to n is in between these numbers. Okay? So when you draw this dispersion relations, when both n is fixed, omega versus k, now it's not a continuous line. Instead, it's going to be the dots, something like this. And in between this and this values, we do not have any energies. That system cannot have that energies. It's corresponding to the omega in between. So we only this dots is allowed for this system. What is the space between those? That space is related to the dimension L. Okay? The space between n equal to 1 and 2, when n is equal to 1, k value is going to be L pi. Okay? When that is a k1, let's say. And then k2 is going to be L of 2 pi. Something like this. So the delta k in between is going to be k2 minus k1, and that is going to be L over pi. So if you have a system very big number L, like centimeters, millimeters, something like that, then the delta k is negligible. It's just negligible. But if you have L in an atomic scale, like 10 to minus 8, like angstrom, something, no? Then this delta k is going to be enormous. It's more than millions and thousands of millions, something like that. So if you apply this intuitively, if you apply this kind of a notion, concept, then you may say, if you confine the electrons in a very small place, like a quantum well means the dimension of this L is going to be 10 to minus 10 centimeters, something like that, okay? Then the electrons can have this much energies, and the next available energy is going to be very much different from the ground states. So when you put some energies outside to excite the electrons to the ground and the next level, then these electrons, when you stop applying application of the energies, then this electron has to go down, return to the ground states. Then when it fall down to the ground state, it has to instantly it has to exert the huge energies, because there's no energy levels available for the electrons to return. Okay, because of this, so that we can have X-rays, lasers, things like that. Okay. So this is the very first step to understand why we do have X-rays and lasers and solids. If this forbidden energies is not there, the energy level is continuous, then the electrons, when it loses its energies, then there is available energy ground to return, then it doesn't have to exert a huge amount of energies at once, like that. Then we cannot have X-rays. One example of that is that when you have a high temperature furnace, in that case we do not have X-rays. Even if you go for very high temperature, like yellow colors, very high temperature, even if you go very high temperatures, you cannot have X-rays out of the furnace. But if you excite the surface electrons, surface atoms of copper with the electric field, then you're going to have X-rays. The X-ray machines is just operating on that principle. Why? Why is that? Why atoms cannot exert the X-rays, emit X-rays, and the electrons and the copper can emit the X-rays? We can understand that the phenomenon with this wave system. So next Monday we are not going to have a class, but on the Wednesday I'm going to explain, I'm going to apply this string, just a simple string wave system to two cases. One,